Hey, so good evening, everyone. Welcome you all back again to the interactive session on system design using Verilog. So this is the week six session that is going to happen for this particular course, right? To introduce myself, this is Ravish Gaurishetty, a PhD research scholar from Indian Institute of Technology, Bombay. As a part of my PMRF deliverables, I'm taking this interactive session for you all. So I hope with these interactive sessions, both of us, like you and me, both of us, will have some fruitful discussions and gain some knowledge, right? Okay. So with this, let's move on to the today's topics. Yeah, so in the previous week, we were looking at designing the controller and the data path unit for a design example, correct? Where we used the ASM chat, like we had designed the hardware algorithm and the algorithmic state machine ASM chat, and followed by the Verilog code for that particular design example. So, as we could not cover this in the last lecture, we will have a look at this binary sequential multiplier. So, this is one of the real time example. Again, I can tell you. So, in this session, we will be dealing with designing a hardware algorithm for this sequential multiplier. So, let us take two numbers a and b, or let's say any numbers. Let's call multiplicand and multiplier, and we obtain the product from the algorithm whatever we are writing, and we write the Verilog code for the same. Okay, so the main motto of this is how you design a data path as well as the controller that controls a sequence of operations for you to get the final ultimate product. Okay, so before going into designing the data path and the controller, as well as writing your own hardware algorithm, it is important for you all to know the functionality, correct? So the first step is, what is your requirement? So in this session, our requirement is to implement the binary sequential multiplier. So we will see what registers, how we are using the registers to implement this particular functionality. Okay, so to understand better, let I initially am starting with one example. Let us take two numbers, 10 1 and 1 0 0 1, right? We call it as a multiplicand and a multiplier. So how the usual multiplication happens in our regular thing is, right, it is a successive addition and shifting of this multiplicand, correct? That is what happens in order to form a final product. So how it does, so initially depending on the multiplier bit, so we look at the multiplier bit. If it is a 1, we just add the multiplicand, right? Or rather, I can say we can just write the multiplicand downside, and if it is 0, we just put it up with 0. It is not just writing the multiplicand here, but we will be shifting the bits by one bit left shift we will be doing, right? So this is a general process which we will do for doing a multiplication. So this requires what this kind of multiplication requires is, it requires a lot of registers and a lot of hardware for this. So in order to store the first partial product, let's call this partial product 1, partial product 2, 3, 4, and 5. To store this partial product, we require lots of registers, and then followed by the addition of all these partial products, which requires a lot of hardware requirement. So in order to minimize that, we can use this Verilog or a RTL coding, where all these steps, the shifting and the addition of the partial products, can be controlled by a controller, right, which controls the operation, how to shift and what to shift. So in this particular thing, what happens is we'll be using only one particular register as a accumulator or the accumulated partial product, let's call the register A, where the partial product 1 2 3 gets updated, shifts, adds according to the control input. So this is decided by the controller. Okay, so instead of shifting the multiplicand to the left, what you can do, whenever you have a multiplier 1, you just put this multiplicand in the partial product. Okay, I'm repeating, whenever you have a multiplier 1, you just put this multiplicand in the partial product, and for the next cycle, whenever the multiplier is 1, you shift this particular partial product towards the right and add to the multiplicand. Okay, I hope you are getting. I'll explain it again. So let us take the example and I will try to explain it. So what we do is, so initially we need the registers to store this, correct? So how many registers are required, and how the data flows between these registers, how the controller control, I will tell you. But after this particular explanation, some of you guys should tell me exactly what states are present, what states are required, correct, and you need to tell me the state diagram from this particular functionality. So knowing the functionality is not your job. So functionality will be given by someone, and once you know the functionality, it is your job to, as a first step, you need to know at least how to write a state diagram. You need to know how many states are present, minimum number of states that can be used in order to implement this function, right? So let's say we have this multiplicand. I am storing it in one of the registers. Let's call it a B, correct? And we have this multiplier. Let's store it in register Q. Okay. So what is the maximum number of bits that the product will have if it is a n-bit multiplicand and n-bit multiplier? The product will be n plus n maximum, that is 2n bits, correct? So for this 2n bits, we use register A and C as a 2n bits. Okay, the register A length will be similar to that of the multiplicand length, and register Q length will be same as the multiplier length. So if it is n and m, so the overall maximum product bits is n plus m. Okay, so what you do is you just check this particular bit multiplier q, let's say this is q, you just check this q of 0, right? If this q of 0 is 1, you just add the multiplicand to the accumulated register, right? So this is one of the thing which the Verilog or the controller should tell. Like, this is the control signal. Depending on the status signal q of 0, your controller should decide whether to add the multiplicand or not. So if your q of 0 is 0, let's say, so then there is no point in adding register multiplicand and register A, right? Because say if your multiplier is 0 here, you just have 0 0 0 0. So even if you are adding, it is again the same thing, but the one thing is you are shifting it. Even if it is a 0, you need to shift the product. So depending on q of 0, you need to decide whether you need to add or whether you need to just shift, right? If q of 0 is 1, you need to add this multiplicand and the register A, followed by a shift right operation, right? So this is the only thing which you need to do, which is the easy thing that I can tell you. Depending on the multiplier, if it is 0 or 1, you need to add the multiplicand to the partial product, accumulated partial product, let's call it the accumulator or the register A. You add the multiplicand to the register A and then shift it, and then shift one bit. then you have a counter here. So how many times you should add or how many times you should shift this. So depending on the number of multiplier bits, if your multiplier bits is n, you take the counter value as n. Let's say you have 8-bit multiplier here, so you take the counter value as 8, that is 1000. These many number of times it should check q of 0, whether q of 0 is 1 or 0, and if it is 1 or 0, you just add this or just shift this. Okay, so this is the only thing that has to be done. So for this, in the last session already we looked at the block diagram. I hope it is it clear till this point. It is just successive addition and
Can
shifting.
you can you explain it once again till here?
The full thing, or you have any particular doubt in this particular?
You like I think you can see the chat box also. Like there are a few questions also. So
Okay, okay. So can I think it's better if you can, if individually you can ask the question, because chat box again I need to go back.
okay, can you just take one a small example and just all the process? Can you just explain it once again?
Correct, correct. Yes, yes, that is correct. So that I will explain it to you in the next slide. So this is what the example we will see here, how you form the final product. Okay. So, but as an initial go, I just want to tell here what are the what are the states it is required, like what registers it requires. So first step in designing is you need to have this block diagram. So what is it with the controller, what you should have with the data path. So data path usually consists of only registers and whatever the values it should store in the registers, that's it. All the control operations that should be given by the controller. So what control operations you require here, right? You require only two operations. That is what my main motive to tell you repeatedly. You require only two operations, that is add the registers. What are the two registers? Multiplicand b and the register a. Okay, multiplicand b and the register a. Anyways, I'll explain you with the example, but here I just want to show you the block diagram. So you need a control signal depending on your status signal. So this is your status signal q of 0. So if this q of 0 is 0 or 1, depending on your q of 0, your controller should give you add or just shift. So everything is decided by this particular controller. Only two operations are here: successive addition followed by the shifting. Okay, so we will see how this happens. I'm explaining you once again here, followed by an example, so that I think it will be more clear. Okay, so I think you all understood this part of this example. I think you all understand this. It is just the multiplication, where if the multiplier bit is 1, you just write the same multiplicand here. Correct? If the multiplier bit is 1, you just write the same multiplicand here, but one bit left shifted. But if the multiplier is 0, instead of writing the same thing, you will populate it with zeros. You will populate it with zeros. And if the multiplier is 1, you just copy the multiplicand here. I hope this is understood to everyone. So finally, you just need to add all these things. Instead of this is one of the procedure. Instead of this, what you can do is, so let's call this as partial product 1, 2, 3. So depending on your number of multiplier bits, so if your multiplier bits is 10, you will have 10 partial products. If it is 20, you will have 20 partial products. So you need 20 registers or 10 registers to store each partial product, or so on. Correct? That is just a one way. Apart from that, if you want, what you can do is you just take one register, let's call it as a accumulator, right? You take one register, let's call it as a accumulator, and what you do initially, you store it with all zeros. Okay, so if your multiplier is 1, what you do, you add these both. That is what we did here, right? The partial product 1 is just the multiplicand. You add these both, and this is what 0. This is again here 0 0. What will you write, the rightmost bit? 0 0 0, because your final product, let's take the final product as c0, let's call it as c0, c1, c2. So your c0 is sum of all the partial products which is at a 0th position or the LSB position. So you will have only this one and all others are 0. So what you do, what is your first step? You add this partial product 1, which is same as the multiplicand, with all 0, so that you get C0. So here what you do is you take a accumulator with all zeros, and if your multiplier is 1, you just add this multiplicand to this partial product, that is 10111. So you add this to this, so your updated accumulator is 10111. Then what you do is, now you obtain this bit, so c0 is obtained. You don't need to add this any further with all these particular bits. Okay, so what you do is,
So we have added accumulator with multiplier or multiplicand.
multiplicand, add these both,
Okay, okay.
right?
Yes.
So now your c0, let's call this as c0. C0 is fixed, this is, there is no change. So you put it aside in some other register, that this is your c0, this value 1. Now again you check with the other bit of the multiplier, and you right shift all these things. So this will go here, this will come here, 0 1 0, right? Now what you do, again your multiplier is 1, so now you don't need to left shift this multiplicand here. In the partial product 2, what you are doing, you are left shifting this multiplicand. Now it's not required, now the relative positions are matched. The accumulator you are right shifting, so you just add this. Now you add the multiplicand, 10111, right? So you will get something, and this is your c1, and this is your c1. Now you obtain c1. So in each and every step, you obtain one particular bit of the final product, that is c0, c1, c2, c3, c4, so on. Okay, and in the final step, it is that whatever the remaining bits are there, that is fixed. So let us look at the example, but just keep in mind that we have this multiplicand, multiplier, and the partial product register. Okay, and this sequence you just keep in mind. We have a multiplier, we have a accumulator register, and we have the multiplicand which we are storing in B. Okay, so now we have multiplicand here, which is 10111, the same example, the previous example itself, which is 23 in decimal, and we have multiplier which we are storing in Q, which is 19 in decimal, right? So now we have this multiplier Q, this is a multiplier, this is a accumulator which is a partial product. Initially we load it with all zeros, and this is the counter which I was talking here. So how many times you need to do this addition and shifting operation? You need to do it the number of multiplier bit times. So if your multiplier bits are 8 or 5, or depending on your multiplier bits, you need to use this counter value. So here we have 8 bits, so your counter value is 8, but in this example your multiplier is just 5 bit, so you write the p register as 101. Once your p register reaches 0, then you are done with your multiplication. Okay, so on every clock pulse you decrement your count register. So whenever you shift this right, whenever you shift this right and you obtain C0, once you obtain C0 you decrement your counter. Once you obtain C1 you decrement your counter. Once you obtain C2 you decrement your counter, such that whenever the counter is 0, that is what your end product. Okay, so let us look at this example.
How will decide the counter value?
Counter value is nothing but the number of bits in the multiplier. So if your multiplier is a 5 bit, then the counter value is 5. See, counter is nothing but how many partial products you will obtain. So how many partial products you obtain in general?
Yeah, here it is like 5 only multiplier,
5.
number of
So your
multiplier.
counter value is 5. So if you have multiplier
Okay,
something like 101, then how many partial products you obtain? 8 partial products, because you have 8 bits in the multiplier, right?
got it.
So
Thank
your
you.
counter is 8. So and you decrement the counter value every time. So once you obtain this partial product 1, you decrement the counter to 7. Once you obtain this partial product 2, you decrement the counter to 6. And once you reach the 8th partial product, your counter will be 0. So if your counter is 0, it represents that yes, there are no more shifting required, and you can just add everything so that you will get your final product. Okay, okay, so let's look at this example. Yeah, initially we store with all zeros the accumulator register. As the q of 0 is 1 here, right, it is 1, so add multiplicand to the accumulator. So the multiplicand is 10111. What you get is this, and you decrement your counter because one addition is done and you are done with this, so you decrement the counter. Then what you do, now you are sure with this particular bit, you obtain C0, so you just put it a right shift. In order to save the usage of one more register, correct, we need a one more temporary register, let's call T, and we can put this value in T. But instead of using one more extra register, what we are doing here, the use of this particular one is done, it is nowhere required. So what we do, we will just put this value in bin, we don't need it, so you just ignore this one and you do this a right shift, correct, and you do this a right shift. So whatever your 4 bits 1001 is there, you get here 1001 right shift, and whatever you obtained as C0, correct, you just store it. There is a empty bit, right, you can store it here. In the next cycle, what happens, you don't require this one also, so you just ignore this, you just right shift this and put this in a bin or somewhere. Now you are left only with 100, so you write this 100 here, and whatever the C0 you are shifting here, whatever you obtain from the next addition 0, you shift here. It is basically shifting and addition, that's it. It is not complex, as I can tell you. It is not complex, just shifting and addition. Okay, so in this fashion, once your counter reaches 0, whatever the value you have here, so this is your final product. Okay, so this is your final product, that is what here. So now I just want you to understand here what operations are being performed. So the controller should perform few actions. So what are the few actions? It does addition operation and it does the shifting operation. Apart from that, is the controller doing any other thing here? You're understanding? Or What is the situation?
Got it now. So there is a counter separately, or it is done by controller itself.
Yes. So the controller itself has only two operations, and you need to write a Verilog code, or let's say state diagram initially. So how many states you need? So what I can tell you is you need only two states. One state is the addition state and the other state is the shifting states, and the other one is the ideal state. It is just the start of this. So in this state diagram you just need two states. Okay, and now you need to know about from which state it should go to which state upon what condition, right? So as you already know, so this is the ideal state, and if you are not starting anything it should stay in this ideal state itself, right? Whenever there is a start happening, then it should go into this addition state where it should add followed by shifting, correct? So this is the
There
simple
is
state
enough
diagram.
lag. Sorry to disturb. There is enough lag. Like if you can switch off the video, I think it will compensate.
Okay, okay, then it will be good. Okay. Okay, I think it is visible now. So it is just you need to know that how what are the states present and what are the state transitions, right? So here you can see we have ideal state, which is an initial state, and the state transition happens from ideal state to addition state. That is when you want to add it, right? That depends on the start signal. So if start is equals to 1, you move from this particular state. So whenever you are moving, what register operations you do, what register operations you do initially when you are moving from S ideal state to S add state, what register operations you do, it is like you need to reset the accumulator, correct? Every time you should reset the accumulator, and you should load the values. Like in the B register you load the multiplicand, in the Q register you load the multiplier, and in the counter register you load the number of bits in the multiplier. So these are the initial steps that you need to do whenever you are starting the count, right? So once you are adding, and then you will shift it, right? You will shift it, or this is just to save one more particular register, right? Instead of having a temporary register again, you just shift it and store in the same queue register, because you don't need this particular one, you don't need this particular one. Once you are done with this, you don't need them. So just use this queue register only to store the values rather than one more temporary register. So it is just that addition and shifting. Okay, and upon every addition and shift you need to decrement the counter value and check if the counter is 0 or 1, right? If the counter is 0, you need to go to ideal state. If the counter is not 0, you need to come back to the addition state. So this is the 0 flag. If counter is 0, 0 flag is 1, right? If counter is equals to 0, 0 flag is 1. If 0 flag is 1, then you need to go back to the ideal state. Yes, the addition, shifting and addition process is done, and this is the final product, multiplication product. But if your counter is not 0, then your 0 flag is 0, right? If your 0 flag is mm, 0, then you should again add and shift, add and shift, add and shift, add and shift. How many times you should add and shift till your counter reaches 0. Okay, so now we will write the ASM chart for this particular thing. Okay, so how do you write a ASM chart again? As already I mentioned, ASM chart has three types of boxes, right? One is the state box, one is the decision box, and the other is the conditional box. So state box is that whatever the state you are in, so that is the state box. So here I'm showing you the ASM chart. So the right side figure is the final ASM chart. This is the initial ASM chart for initial understanding. So both are same, but here it is the right side ASM chart has the complete control path, whereas this does not have the complete control path, rather it just showing the register operations. So let us directly look at this right side ASM chart, where we have three states, right? As we already looked into idle state, addition state, is add, as shift, correct? So you should go from idle state to addition state whenever your start signal is 1. So this is the decision box. But before going into the addition stage, you need to, as I already told, you need to load the register. That is, accumulator you need to reset, multiplicand store in the B register, multiplier you should store in Q register, and carry bit also you need to reset it. And the this is the counter, P is the counter, you should store it with the multiplier size. So these are the initial register operations which you need to do whenever you are going from idle state to the addition state, correct? Once you are in S idle state, upon every clock pulse till the counter value is 0, you need to add shift, add shift, add shift, that's it. So what you are doing here, you are writing here add register and followed by shift register. So you should check the Q of 0, that is the multiplier bit. If it is 1, then only you add, otherwise you directly shift it, correct? Because addition with 0 has no meaning. So instead of repeating the operation, you just directly shift it so as to reduce the load on the hardware, right? If your Q of 0 is 1, you add and then shift. But if your Q of 0 is 0, you directly shift and you check for the 0 flag. If the 0 flag is not 1, if the 0 flag is not high, that is the counter is still not 0, you again add and shift. Okay, until and unless you see the 0 flag goes high, you go into this idle state. So now we will write the Verilog code for this particular ASM chart. See, once you are done with this ASM chart, Verilog coding is nothing, I can tell you. So it is just writing this ASM chart and the state diagram, that's it, correct? So I think now it should be easy for you guys. So it is just addition shifting from the ideal state. So how does the Verilog code look like? You need to have separate controller. You need to have separate data path unit. What the controller should tell you in the Verilog code? It should tell you that if you are in this particular state, okay, it should check the status signal, should check in which state you are. If you are in this particular state, and if your start signal is 0, the next state also you be in this particular state itself, right? This is what the single step I can tell you what you should be there in the control unit. Yeah, so this is the control unit. So if a reset, right, if you are in reset state, stay in the ideal state itself, don't go to next state. But if you are not in, if your reset signal is 0, then you go to the next state. Okay, If you applied reset, be in ideal state. So this is your first step in the behavioral coding, correct? And then what you do, this is the case statement. As I told you, it is very simple. You just check the state. If you are in ideal state, depending on your start, if start is 1, you move to the next state is add. Otherwise, be in the same state as ideal. Okay. If you are in s add state, now once you are in s add state, your next state should be s shift state, and you decrement the p, right? Once you are in s add state, you decrement the p, and you should go to the next state. Whether you add the register or not, that depends on q of 0, right? So that you will write again. So that you will write again. So that you write here. So if q of 0, so depending on your q of 0, if q of 0 is 1 or 0, your add register will be 1 or 0. And if your add register is 1, so this is what the control unit job, it just tells that add register is 1. What should be done if add register is 1, that is the data path unit, because if add register is 1, the register value should be changed. That is the part of the data path unit. Okay. So you just check here, if q of 0, add registers. Similarly, if you are in state as shift, what should be your next state, right? So these are the basic things which you write once you understand this particular ASM chart. And what is the data path unit? Data path unit tells that if your add register signal is high, right, this is what you obtain from the control unit. So control unit tells that add register should be high or low. What it should do, if add register is high, you just add it. If your shift register is high, what you do, you just shift right. You just shift right. And if your decrement p control signal is high, you just decrement the counter. So that is what the functional block tells you basically here, right? So controller will tell whether to shift register, whether to add register, whether to decrement p. And depending on this shift register, if it tells high, if it is high, then you just shift it. Add register tells high, then you add both register a and the multiplicand. That's it. The data path unit job is just listen whatever the control signal is telling, and also it sends the status signal. So q of 0, once this job is done, it adds a and b, and it shifts this q register, right? And it shifts this q register, it will send the status signal to the controller. Yes, now my q of 0 is 1, now my q of 0 is 0. So it sends the status signal. So depending on this q of 0, again the controller will decide whether it should add or not. So that is what you write it in the control unit. Depending on your status signal q of 0, so the controller will tell you the next step, whether to add or not to add. So by default, you are writing it as add register is 0. So if your q of 0 is 0, then your add register will be 0, and your data path unit here, add register will be 0, and your data path unit will not add, right? It just shifts. That also you will get the command from the controller that you should have a shift register as high. So as soon as you go to s shift, your shift register goes high, right? As soon as this shift register goes high, you will see a shift in the multiplicand as well as the, not multiplicand, multiplier as well as the accumulator. So this is the multiplier, this is the accumulator, right? So this is the basic controller and the data path unit functionality, what I can tell you. Now what we do is we will see how to what a test bench. Most of the topics I think covered in the last week sessions were related to the test bench, right? So we use the test bench here. So this is a test bench. These all things were explained in the class, like how you define the module where you don't use any parameters, how you define the inputs and outputs here. So it would be the opposite, right? So the inputs would be of the registered data type. So I think these are all covered in the lecture. So you will instantiate whatever the module which we have written, Verilog module, you will instantiate, and for the testing purpose you just send all the values. What should be your multiplicand? Your multiplicand is 10111, as we have seen in the previous example. Your multiplier is 10101. That is your multiplier value. So it just sends the values: multiplier, multiplicand, ready if it is 1 or 0, clock. So what you are doing, so this is one initial block where you are sending all the signals, and this is another initial block where you are repeating 26 times clock is equals to not clock. So 13 times you say a positive edge clock. So whenever you say a positive edge clock, you have written in the Verilog code that your control unit should generate some signals, whether it should shift or add. That particular signal should be sent, and the data path unit should update the registers. So that is what you can see here, right? Initially at time 5 seconds, so you have, after every 5 seconds your clock goes. So for 5 seconds, 15 seconds, 25, you see a positive edge clock for every 10 seconds, right? Your counter is initially 5, the number of multiplier bits, and your accumulator is a, multiplier is this value 10011. So what you do after the first clock cycle, according to the code, it should add multiplier as well as this multiplicand 10111. You add this 0000 to 10111 and you store it here, right? And you decrement the counter. Upon next clock pulse, you just shift them, right? You just shift this 1001, you shift right, and this particular one you write it in queue of MSB. So this is what you do until and unless you see a counter is 0. Once your counter is 0, that is what your end product, right? So your end product is this. So that is all for today. I just want to share you the binary multiplier thing and how to design the data path unit as well as the controller for the same. I will upload the slides also in the same, and you can follow it over there. Okay.
Thank you.
Yes. Thank you.
Thank you very much.
Okay. Thank you.